Hello, everyone. I'm Islam. I'm a senior software engineer at Netflix, and I work in the big data compute team. So our team deals with the compute engines such as Crano, um, Spark, and some other ones. And we take advantage of open source tools such as the ones that I've just mentioned, as well as some of the commercial offering for different needs of the data warehouse at Netflix. Okay. So this talk is particularly about our experience in speeding up some of the interactive use cases that we had from some of our clients and their needs and kind of how we got started. And as Brian mentioned, there are a lot of different ways to cache things, and this is just one of them. And I'm going to tell about our experience and how we benchmarked it and what worked for us and what didn't work. And also a little bit I'm going to touch on the cost side of the equation as well. Okay. All right. So I'm going to start with kind of talking about the modern data warehouse architecture and how it looks like in the context of Trino and compute engines like that, and what it means for the users that expect interactivity from their queries. Okay. So basically, data warehouse data needs have grown exponentially since pretty much when computers were introduced. And it was noted that data growth is actually much faster than the compute needs. So, different from, let's say, the first version of the data warehouse where we had, let's say, HDFS nodes kind of usually collocated and doing both data serving and also compute. The industry has trended towards disaggregating storage and compute. And why is that? Because different use cases can be skewed towards, let's say, storage needs if you have a lot of needs for storing a lot of data, or sometimes you can have a need of very intense computes if you're running some mathematical equations or possibly some very advanced A/B testing techniques or anything like that. So what this allows us is to kind of disaggregating these two components of compute and storage allows us to be more cost saving and efficient. And it also allows us to scale them separately, horizontally. So we can you can think about it as like adding more machines on the distributed file storage to support growing data needs, or just adding more worker nodes, let's say in the Trino installation, to speed up some of that compute that you need to be done on the data. Okay. Another component to this equation that we've got is the metastore, which usually is implemented as a, let's say, database. It can be MySQL or CockroachDB or anything like that. And it's just a simple way to think about it is just a centralized store where we keep kind of bookkeeping of our metadata of the compute. And it also can be distributed, but in this case, let's just think about it as something simplistic that we just talk to and we get our metadata request answered. Okay. And in this talk, we're going to be talking about mostly iceberg connectors. Iceberg connector of Trino. That's where we conducted our experiments, and that's, at Netflix, iceberg is taking kind of the center stage, and Hive is kind of like getting less and less use. So that's just something that we've used. And okay, so if we talk about this architecture now, kind of like disadvantages, what are disadvantages of disaggregating the storage and compute? The disadvantages, of course, that they have to now communicate over the wire, right? They're not collocated anymore. So whenever you access data, you end up issuing requests to distributed file store. And for example, we use S3, and S3 can be sometimes unpredictable in its latency. Some requests can take, hundreds of milliseconds, and sometimes it can take like even seconds to to complete your remote request. So this is not acceptable for the interactive use cases. And why is that? The reason behind that is that the data warehouse provides this kind of cheap way to deal with a lot of data, and it also kind of is, with the help of Trino, it's on the kind of cusp of interactivity. So a lot of our clients, they're building dashboards and A/B testing tools on top of that. And for them, let's say the difference between 5 and 10 seconds can mean a context switch of a user, and that's very costly. So if a user kind of goes away from their tool and start doing something else, and then that basically results in like lost productivity. So these clients are very much interested in reducing latency. And in this talk, I'm going to talk about several layers of caching that we've introduced into Trino, that we use at Netflix, and as a kind of a research project that we're planning to roll out in production in the future and contribute it back to the open source. And yeah, I'll talk about our experience. Okay, so let me go to the next slide. Okay, so the answer in our case was to how to do caching right. So of course, just let's add some caching, right? That can almost sound obvious, but how do you do it right? And which places do you need to be caching, and which parts you shouldn't be caching, and how you should be caching it so that, the hit rates are high, and, you don't have too many cache misses. And also like being cognizant of the costs. So you don't want to ship something that's very expensive, and then it's not just going to make sense for, let's say, our users to use this instead of maybe switching to some commercial offering, some other database that does these things for cheaper, maybe at the same speed, or maybe a little bit less speed, but it does it cheaper. Okay. So in our case, we basically added several layers of cache to speed up the interactive queries. One of them, the simplest one, is the RAM cache, where we cache some bits of metadata, and we also utilized EBS SSD volumes that are optimized for I/O and have predictable, let's say, latency compared to a cheaper distributed file store such as S3. And we cache a bigger chunks of data in there, and I'm going to talk about what exactly we cache there. And another component that we've added is, avoiding some of the computes that is being done over and over again, such as, accessing file footers for Parquet files, and, parsing them over and over again, especially for queries that end up touching the same files. That was just kind of wasting both CPU and contributing to latency. Okay. So basically, these caches, what they do is they end up kind of hiding the inherent latency of the disaggregated architecture of the modern data warehouse, which helps to make interactive queries a little bit faster. Okay. So let's talk about the Iceberg connector and in general caching of the metadata. All right. So Iceberg connector is kind of interesting in that it. So let's say in our normal Hive, we don't keep a lot of metadata on the distributed file store, right? We keep them in the centralized Hive metastore that I've mentioned, or it's a separate database that can do certain operation faster, and usually it's faster than distributed file store. But in case of Iceberg, there are metadata files, manifest list files, and manifest files. All of them are stored on the S3. And let's say from the metastore, we only have like, a very lightweight operation of kind of getting the current metadata pointer. And for Iceberg, it was even more kind of important to cache these files in the S3, because for bigger, larger tables, or tables that see a lot of writes or a lot of modifications, these manifest files and manifest list files can be quite non-trivial. They can get quite big in size, in megabytes, and caching them was very important for speeding up the query planning stage, as well as the scan and project stage. Okay, so in our case, coordinator caches the metadata on a SSD EBS volume. And in this case, why is that effective? It's effective because snapshots are immutable. So you have each snapshot that is kind of ends up as a map of files on DFS, and whenever you add a new snapshot, it never modifies the existing files. It basically adds more files, right? So each snapshot basically maps to a set of files, and whenever you refer to a given snapshot, you basically can cache those files, and you can be confident, that these files are not supposed to be changed, they're not supposed to be mutated. So it's very, very effective to caching them, and especially caching metadata. We've seen a lot of benefit in our use case. Okay, so we have coordinator node, which is pretty simple. You just have one node, and caching for that, it's kind of straightforward. And for the workers, it's a little bit more complicated, because usually how we do kind of scheduling on the coordinator. So after this SQL planner and optimizer phase, we need to do scheduling. So it means that we end up getting table metadata, getting partitions metadata, and we end up generating units of work. We can call them splits, or basically what they are files to be read from the DFS. Okay. So if we kind of distributed these files in a fashion that just optimizes for worker utilization uniformity, like we normally do, that would mean that we'd sacrifice cache hit rates, and we'd, let's say, schedule the unit of work 91 sometimes on worker number 1, sometimes on worker number 2, and sometimes worker number 3, almost random, and just based on that worker's utilization. So what we ended up implementing and making it kind of more configurable, and allowing ourselves to have either kind of a flexible affinity scheduling policy or more hard affinity policy, is we grab these units of work, and we kind of generate a hash of it. So in a simple way to think about it is that a unit of work is usually a file that has an offset and a length to be read, right? So based on the path, offset, and length, you can generate a hash, right? So for this hash, we actually want to only use the file path. We don't want to use the offset and length of the file, because we want to, different works, they're going to do different parts of the file, but we want them to kind of like go to the same worker. So anyways, in this diagram, we can see that sometimes it can mean that the load on workers is uneven, and we're aware of this, and because that's not something that we optimize in. But what we saw in production is actually we haven't seen high rates of non-uniformity of the load on workers. And we also ended up using more flexible affinity scheduling policy, in that for each unit of work, we usually have 2 nodes that we schedule it. One is the primary node, and if that node is experiencing some troubles or is too overloaded, we end up going to a secondary node, secondary worker node, and scheduling it there in the cases if first node goes down, or it experiences high load. So affinity scheduling allows workers to have isolated caches from each other, so they don't have to communicate. So if you think about it, let's say there are other ways to cache data that we've seen is, for example, Rubik's cache that has a bookkeeper on the coordinator node, and it also has the Rubik's instances on each of the worker nodes. And in this case, you don't need to modify the Affinity scheduling. You don't need to modify your scheduling because basically worker can reach out to the bookkeeper service, can ask, hey, where is this file cached? Or where is supposed to be cached? Then it goes to that worker and checks it there. And if it's not there, it goes and gets it from S3. But in this case, you have overly chatty workers kind of like issuing network calls to with this bookkeeper service and checking which worker the file is cached on. And that's just something that didn't work for us. And we ended up kind of going towards implementing Affinity-based scheduling and implementing kind of isolated cache for each worker. In this case, they don't have to communicate. Okay, so first cache that and the simplest cache that we introduced is the FileStatus and the Parquet footer cache. So FileStatus cache, so before it's something very simple, and it's just a cache in the RAM of a given worker. So let's say worker needs to read that file, right? So from S3, what call does it need to do before even accessing that file? It basically calls get S3 object metadata, and this is just one of the snippets from the profiling of latency profiles that I've done, and you can see that basically 95 maybe percent of this call is just waiting for the network. It's not doing anything useful, and it's just not getting that metadata, you can't like really read the file. You can't open the file. It's basically caching the file descriptors, right? So caching them doesn't take a lot of memory and is highly effective in reducing latency, especially making latency more predictable. Let's say dealing with S3. All right. With the footer cache, it's kind of a similar story. So before you read a Parquet file, you need to basically access the footer, and you need to parse it, and you need to figure out the stats and to understand which chunk of the file you actually need to be read, which chunks can be pruned, which chunks you actually have to read, or maybe like you don't have to even read the whole file at all, right? So this is a similar story. We just throw these Parquet footers in the RAM cache, and the cache has a configurable capacity, and it uses LRU. So the hottest files are always in the cache, and the files that are accessed less often, they kind of get evicted over time, and it's just an efficient strategy to deal with this. And of course, this is possible with the Affinity scheduling, because every time you read that file, it's read from that worker node, and that worker node usually will have already information about this file, the metadata in its cache on memory ready. So it doesn't need to go and make that RPC call and introduce extra latency. So I wanted to check if these results kind of hold up, if they're statistically significant, or is just like something that we see on the benchmark, or like are they actually applicable in the real world? So we ended up setting up 2 clusters, control and test, and running same queries over and over with configurable repetition. And what we ended up doing, we wanted to see how do these play out in our production traffic, not on some sort of a synthetic benchmark. So even these simple metadata caches, they can bring up to like 10, 11% latency reduction. They're very easy to implement. So the probability that it performed, it reduced latency for 8%. It's very high. It's more than 99%, and that was just a very easy decision to just ship that, right? So there are also additional CPU savings because we skipped serialization, deserialization of the footer nodes. So that's just bringing some extra additional improvements there. Yeah. Okay, so now we can go to the next step. So the next step is we're gonna touch a little bit more here. So for the data files, what do we do for the data files, right? So Parquet files, they can be quite a bit larger than these bits of metadata that I've talked before, and fetching them from DFS sometimes can take a long time. And what did we end up doing here, right? So in this diagram, you can see our kind of final solution with the SSD IO optimized EBS volumes. So we ended up using for the prototype a library called Alexio. So Alexio is a data orchestration kind of software that is kind of similar to Rubix that Trino already has, but it also has a capability to serve as a library, right? So you can just stick it between your file system and your worker node. And basically what it will do, if you provide it, let's say you pointed towards a volume that you can use for cache, it will, on request to read that file from the S3, it will read that file and then it will put it in the cache so that the next access is going to be much faster. Okay. And this system is pretty advanced in that it has some pretty good optimization. So one thing that it does, it basically divides files in chunks. So the default chunk is 1 megabyte, but you can set them to whatever suits your needs. We found that 1 megabyte worked pretty well for us. Both for metadata, as I said, for the iceberg metadata, manifest list files, and also the data files, the Parquet files for workers, and the metadata files, they were for the coordinator. They are Avro files in our case. Okay, so so the Alexio library splits your file into 1 megabyte chunks, right? So for example, if you want to read from let's say 0 to 3.3, it will read 4 1 megabyte chunks, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Okay, and let's say if you have another request and it needs to read a different part of the file with the offset, the length per meter, as we have discussed before, it will the chunks that are already on the SSD cache, it will grab them from there, and the chunks that needed, it will be fetched from remote storage and cached. Okay, so you have cache misses that go to the remote storage distributed file store, and you have cache hits that go and grab the data from SSD. We actually experimented, we had 2 experiments. So one was to use SSD EBS volumes, and another one was to use workers that have SSD drive in them. Let's say you grab a worker instance, EC2 instance that has, let's say, 1 terabyte SSD, right? So what we found with EBS is that it's a little bit slower than having, let's say, workers with dedicated SSDs, but it's much faster. It's much cheaper. Sorry, it's 5 times cheaper than having dedicated SSDs with workers. And the thing with EBS is that you can scale it independently. As I said, sometimes you want to have a big cache, but you don't want to have a big compute. You don't have that compute requirement, right? So you can scale your EBS volumes, and you can still have like fairly small worker pool, but just has access to the EBS drives. And also you can speed up EBS even more. You can, let's say, attach several EBS volumes to one worker and put them in RAID 0, and then your speed of access will be even faster. So in our case, we just ended up attaching GP3 SSD volumes to each worker node, and that was pretty good in terms of battling with latency, and it was also pretty effective in terms of cost. So we ended up not spending too much money, but getting majority of that win that we would have gotten with the dedicated SSDs, and we ended up basically shipping that in our benchmark, and I'll talk about the results later. But of course, with this kind of having these files so much closer and so much more consistent to the workers, you just end up with like huge wins, especially on the warmed up queries. When you have your warmed up cache and you end up kind of like reading the same data, it's just order of magnitude 2 or 3 times faster than going to SSD. Okay, and the last cache that I'm going to talk about is the query fragment cache. And we borrowed this idea from the PrestaDB. They've done this work on the RaptorX. So what this does is basically imagine that you have a query, some query that basically computes a sum for some given partitions, right? And you push those units of work to your worker nodes, and you push that computation, that aggregation that each worker can do. So once that work is done, you can cache that result again in that EBS SSD volume that I talked about. So with the fragment result, you know, it's a little bit more kind of targeted towards these dashboard cases where you have, you know, kind of similar filters, similar slice and dice use cases, drill downs, and your query shapes are not as wildly varied as, you know, as if you just gave like a command line and people just entering their queries in any way, shape, or form, right? It's usually, in our use case, was exactly that. It was the dashboards that were powering UIs. So UIs were being powered by the Trino queries. And we found that this was very, very effective for us. So you don't have to do your scan, your aggregation. You just go directly to compute. You go directly to your cache and you grab that computed result for that given worker, and you just return it very, very quickly. And this was very effective for our A/B testing framework, and A/B testing framework's UI that is powered also by these Trino queries, because there we had a lot of compute being done on the data, and that being able to, and it did a lot of aggregations as well. And the worker nodes on Trino, they can do each worker will do an aggregation, a partial aggregation result, and caching that was just saving us a lot of the latency. So it was useful for certain use cases, and we ended up including this in our caching architecture, right? So to kind of benchmark this in a way that I wanted to throw the hardest ball at this caching architecture, and I basically like added all these caches: metadata cache, footer cache, Alexio data cache, both on coordinator and worker. And the hard kind of part for this kind of cache is that we don't want the queries to repeat, right? That would be hard for this cache to show any improvements on. So we just grab the data from the previous day, all the queries that were run on our ad hoc cluster, not even on our dashboard cluster. Ad hoc cluster where people just can go and just write their queries with their hands, type them in and submit them and just do exploiter analysis, right? So we just grab all these queries, real traffic, and if some of them repeat or some of them naturally tend to touch the same files or tend to, let's say, do the same computation, we're not going to fake that. We're not going to run every query twice or 3 times or 4 times to kind of make it easier or like make our results look better than they are, right? So replaying this production traffic on both control and test clusters allowed us to sometimes hit 2x latency improvements for certain queries, but with very high kind of confidence and with significance, we could show that we can easily expect 30 to 35% latency reduction in the queries that we that in the worst case we do with the ad hoc queries. And this solution we more or less target towards our dashboard use cases where same queries can be repeated by different users over and over again, kind of going to the same screen. And there, improvements can be even more. But this is kind of the worst case that we wanted to kind of address and be aware of, that at least there's no negative effect, right? And for just queries that we grab from one of our dashboard use cases and we ran them like one by one, we've seen sometimes 3 times faster improvement. And again, these are queries. Some of them they do more compute than the others, so there you can see that the effect of caching is not as strong. And some of them they actually repeat and they grab the almost the same. They touch almost the same files that were already cached and computed. And for those queries, you get really good performance. And yeah, so that's kind of the results that we've got. And that was the proof of concept project that was just a couple of months. It's not a lot of work, and we're planning to polish this up, and we'll very likely will use this in production because we're very, very confident in the improvements that it produced, and also in the costs, and it just kind of like clicked for us. Okay, that's pretty much it. End of my presentation.